be covering area, and then the next topic I'll be discussing will be volume. So we'll cover not the entire volume, but a little bit of volume. Okay. Now, any question on example 3? Now let's do example 4. Example 4, example 4 is 2 parts also, dx slices and dy slices. Okay, so let's look at example 4 here. Maybe I'll do this one a little bit quicker, but example 4 is a little bit more interesting than example 3. Example 4, find the area bounded by x equals y plus 2 and x equals y squared. The 2 equations. So first we want to graph these and identify the region. So what is the region here? So let me just graph this manually. If you graph it, then this is how it looks like. Let me see. Let me clear. Make this thinner, and let me use black color here. Okay. So the graph, if I do a rough sketch here, the rough sketch of the graph kind of looks like this. This is y is equal to x equals y squared, kind of looks like this. This is x-axis, y-axis. This is y equals x squared. This is kind of like y equals x squared, but this is x equals y squared. So the graph of y equals x squared is reflected with respect to my y equals x. So we end up getting a graph like this. And then the other graph is x is equal to y plus 2, which is the same as y is equal to x minus 2. Y equals x minus 2, yeah, it's not hard to understand. Y equals x minus 2, the graph is going to look like this. So this line is y equals x minus 2. So this is, again, y equals x minus 2. And this graph is what? This graph is x is equal to y squared. Note that this graph and this graph put together, this is x is equal to y squared. But if you just pick the top half only is y is equal to square root of x. The bottom half is y is equal to minus square root of x. Once again, the bottom half is y plus minus square root of x. The top half is y plus square root of x. And this y plus x squared, what is that? That is y x squared, x equals y squared is the graph of 2 pieces combined. Okay? So when you combine the 2 pieces, that becomes x equals y squared. So we have to know this on this problem. So that's what it is. So now let's see. Why don't we do this here? First, let's try to do this by dx. So first of all, we have to identify the region. So what is that point? That point, by the way, when you actually solve the equation, it turns out that point is actually 4, 2. So we need to know that point. And then this point right here, obviously, is the origin. So that one, I don't need to mark anything. That's the origin here. That's the left-hand point in some in. Then this right here, what is that point? That point is actually what? It's actually 1, -1. So how do you find the points? How do you find the points 4, 2 and 1, -1? Maybe I didn't do that here, but in this case, to find intersection, so you maybe can do this here. Okay, so let me write this here. How about this? To find intersections. To find the intersections of these curves, what do you do? Let y plus 2. So all you have to do is what? Y squared. How about this? Y squared is equal to x y plus 2. So we can do that. So we get y squared is equal to x equals y squared and x equals y plus 2. So we can equate the 2 x's and then we get this. So what we end up getting is we get y squared. We get y squared and then what? Minus y minus 2 is equal to 0. Then we can factor that out. Factor out? Yes, we can factor that. And if you factor those, what do you get? We get y minus 2. And then times y plus 1 is equal to 0. Yes? Is that right? Yes, that fits. So y minus 2 times y minus 1 equals 0. So what is that? That implies that y must equal what? 2 or y is equal to negative 1. Okay, so now I don't stop here. Now let's actually find the point. X equals y squared. So we get the point 4 comma 2. And if y equals negative 1, then what do we get? X equals y squared. So you get 1 comma negative 1. I like to spell everything out so that when I need it, I will have it. So try to write everything you need before you need them. This is what I recommend. So now, what is the reason here? The word reason cannot dx slices. The first we go by, why don't we try to do this by dx slices? Now, is dx slicing and dy slicing always possible? This is a very important question here. Is dx slices and dy slices always possible? So dx slicing and dy slicing, is it always possible? And the answer is, I'm going to answer that question a little bit later, all right? Not all problems can be done by dx slices and dy slices. Some problems, they can only be done by dx slices, and some problems can only be done by dy slices. And some of them, like this one here, they can be done by both ways. Although one method is actually easier, in this case, as I see it, the dy slicing is actually easier, as you will see. Why dy slicing is easier? Well, you'll find out, okay? I'll show you why. And if you still like dx slices better, then you can do dx slices. I'm not going to stop you, all right? So now, let's see. Let's say we'll do this by dx slices. So the first thing is, we're going to try to find the area by dx slices. If it's dx slices here, then how will the rectangle, the slices look like? The slices is going to, the slices, let me see, the slices will look like this. And will be like this. So this is how the slices will look like. Maybe I should maybe draw this in black. Maybe I'll reserve the red color. So now how about if I do this in black? Okay, so the slices will look like this. This is by dx slices. Will look like this. Now, and this is by when x equals 1. When x is less than 1, the slices is going to look like this. You know what? The slices will look like this. So this is how the slices will look like when x is less than 1. When x is bigger than 1, the slices will look like this. Now the reason why I drew two slices is because let's look at the upper boundary function. What is the upper boundary function? The upper boundary function is this right here. The upper boundary function, let me mark this in red. The upper boundary function is here. So this one, the upper boundary function is over here. So this side. Now let me now mark the lower boundary. That is what is the bottom of the rectangle from 0 to, this is from 0 to 4. So from 0 to 4 looks like that's the error question. So when between 0 and 4, what is the bottom of each rectangle? The bottom of the rectangle, let me mark that in green. It will be here. And this will be here. Now, because this is in dx slices, all the equations, solve for y in terms of x. We have to now we have to get the equation y for something else. Y for something else. Now, what is the upper boundary function here? Now, if you look at the upper boundary function here, let's see. Let's look at this guy right here. And let's look at this guy right here also. What are they? Upper boundary function, y is equal to square root of x. The given equation is x equals y squared. But now, the equation we need, the form of the equation we need is y equals square root of x. That's what we need. Because we have to solve for x. And this is now the top of each circle. So this one, we need y equals square root of x. That's what we need. We don't need y equals minus x for now. The top of each rectangle is y equals square root of x for that point and that point. For both red points, the upper boundary function is y equals square root of x. So now let's look at the lower boundary. Now when you look at the lower boundary, we have a problem there. Why? Because we have a point here, which is, let me now mark this in dark, is right here. And then we also have a right here. But this point and that point, they are actually part of two different curves. They're not part of the same curve. They're not part of one equation. So this point right here is actually on the line. The line we have is y equals x minus 2. We have to solve for y. Solve for what? Solve for x. Solve for y. So in this case, we do have y is equal to x minus 2. So y must be solved. So solve in terms of x. Now what is this guy right here? The green dot on the left side, when x is between 0 to 1, this guy is actually y is equal to minus 4 of x. Now, does everybody follow here? So, what happens is, at x equals 1, it divides. The lower boundary curve, so here, now let me write this down. When x is between 0 and 1, the lower boundary curve is y is equal to the square root of y is equal to minus 4 of x. But when x is between 0 and 4, then the lower boundary is y plus x minus 2. There's an equation change. Equation is different. The lower boundary for x equals x between 0 and 1, and the lower boundary for when x is between 1 and 4 are different. But the upper boundary functions are the same. Upper boundary function is both good. But because the lower boundary function is different, now we have to split this. So in this case, let me use a purple here. So we have to split this at this point. Split the interval. At this point here, now we have to split the interval right here. At the purple line, we have to split. Why? Because the lower boundary equation is different. Again, the lower boundary function is different. And because there's a difference in the equation, this is the reason why we have to split. We're not splitting because there's a corner at the bottom there. It doesn't matter how it looks. But we have two different equations. So, integral from 0 to 1. So let's look at this. Integral from 0 to 1. From 0 to 1, the upper boundary function is y plus square root of x minus lower boundary is this. Now we have a double negative here. This is the upper boundary. And minus the lower boundary. And then we have to subtract it. So we end up getting a double negative. So we end up getting this when you simplify. Now from when x is between 1 to 4, again, the slicing direction is dx. Very important. dx. dx. Slicing direction. Very important. When you set up an integral, whether that be area or volume or length or surface area or force or whatever you talk about, in all kinds of applications, when you set up an integral for those things, what is the first thing you have to go? The very first thing you have to determine is the slicing direction. The slicing direction is not hard, but if you mess up in the slicing direction, the problem will be irrecoverable. You will mess up the problem. Again, if you get the slicing direction incorrect, then what happens? The entire integral will blow up immediately. Is that clear? So this is one of those steps which is easy, but very important. So important that the integral will get messed up if you do not get the slicing direction correctly. Slicing direction is the first one to go, the most important, easy step. It's not the hard step though, it's an easy step, but terribly important. It's simple, but important. Easy and simple, but important. Now the interval, from 1 to 4, the upper boundary function y equals square root of x minus the lower boundary function y equals x minus 2, and there we go. And that is now the interval setup. And the rest of it, you can compute, and then the final answer looks like you do get 4.5. You get 4.5? Yes, you do. Does anybody have a question on this dx crisis? Does anybody have a question here? Pass? Any questions? Any questions here?
No.
Okay, now we will now discuss the dy slices. And as you will see, the dy slices is actually easier. I know. I think the students, they like dx slices. When it's dy slices, the students, they hate this, right? And that's because the students are not used to it. But for this problem, example 4, the dy slicing is actually going to be easier. And so this is something you have to know. And again, sometimes the dx slicing is easy. Sometimes the dy slicing is easy. Sometimes only one way is possible. The other way is not even possible. And I will tell you exactly when this is possible, when this is not possible. Okay. So let's just do the dy slicing this time. So in this case, what do we do? The dy slices. Same problem here. Let's go by dy slices. So I'm going to save this, and then now what I'm going to do is I'm going to clear some of the what is it? I'm going to I saved it. Did I save it? I saved it, and I'm going to undo this. So that I'm going to work on this. I'm going to keep the same diagram. Okay, so let me keep the same diagram. So we have this. Okay, so now what I'm going to do is, let's see, how much do I have to go back? Okay, I think that's good enough. So now what I'm going to do is the dy slices. Okay, let's do it. By dy slices, the slices are going to look like this. Let me now use orange here. The slices will look like this. How about, you know what? Let me just like a thick marker. I'll just use a thick marker, and I'll use orange. So dy slices, I'm going to draw a slice right here. So maybe a slice right here. So the slices are going to look like this. Actually, it's passing through right here at y sub k, not y sub k minus 1. But anyway, you know what? This will be a rough sketch. Now let's see. The right end of each rectangle for these horizontal slices will be, I'm going to mark them in red. You know what? How about this? Let me erase the red and the green. Oh, I'll do that. Can I erase red and the green? Oh, now I cannot erase the green. Can I? Oh, can't do that. It's hard to erase the green now. Oh, there, I did erase. Okay, good. Okay. So now I marked and I drew the slices like this. Now this is dy slicing. So the slices will look like this. The height is dy and the length will be like this. Okay, now let's see. Now let's look at the right end point of all the slices. The right end point of all the slices will be over here. The right end point will be here. Let me write them in red. Let me mark them in red over here. That's the right end point. And then this one over here. So whether the rectangles over there on top or the bottom, as you can see, they're part of the same curve. They're all part of the line. And even if the rectangle is over here, so let's look at this. Even if it's over here, you will still get the same thing. Doesn't matter. So the right end point is the red dot. So how do we now get those? Now this in terms of this is a dy slices. That means all x's. Now let me write this down. All x's. All x must be solved in terms of y. So that everything will be entered in terms of y, not in x. The entire integral will have x only. All right. So in this case, if you look at this, what is the right end point? The right end point is the red, and that will be now what? That will be now red. Let me write it down. Excuse me. So the red will now be this right here. Will be let me write this down. Red here is going to be x is equal to not the orange. I want the red. So x is equal to now what? Sorry, x is equal to y plus 2. So the right boundary function is now x equals y plus 2. This is the right boundary function. Right boundary is kind of the upper boundary because it has the one with the higher x value. And then the lower boundary, in this case, I call this the left boundary. The left boundary, I'm going to mark it in green. This one and that one. But as you can see, both midpoints, they both lie on the same curve. And that is what? That is still x equals what? Y squared. Oh. So we have only one upper boundary function, one right boundary function, and we only have one left boundary function. And therefore, in dx slicing, we have two intervals, but when you go by dy slicing, we don't get two intervals, we only have one interval. We only have one interval, that's it. And so what is the interval going to be? The interval is going to be like this. Interval from where to where? Interval is going to be from y equals -1 to 2. What is the right boundary? The right boundary is the x is equal to y plus 2. And then what is now the left boundary? The left boundary is x equals y squared. So this, and then what's minus y squared, and then dy. So the area in dy slicing is going to be this guy right there. Do you have any questions here? Any questions? Now what I'm going to do is I'm going to save this page, and then now what I'm going to do is, how about this? Without erasing, let me just scroll this down a little bit, and then if you scroll down here, yes, you can see, and exactly that's what you see right there. Yeah, so the interval you see right there. But now everything's kind of messed up here. Okay, but see. But anyway, that is the that is interval you see right there. Any questions here on example 4? Well, let me clear all this. Any questions on example 4? Yes or no? Now let's look at example 5. Now example 5 is now going to tell us which slicing direction is possible. Okay? So example 5 will now answer the question. Finally. To find this area, which slicing direction is possible? Example 5 is now to answer that question. Now, when you look at these two equations here, they both solve for x. When looking at the two curves, the two equations, x is what? X is solved in terms of y. This means dy slicing is possible. Now, the next question is this.
Yeah, hon. We weren't losing power. It was the internet. blinking on. It's blinking on and off. We're losing service. Really? Where it could be something to do with next door construction. I don't know.